made a point that I thought was interesting. So, yeah, no problem. Credit where credit is due. So they were working on the water, standard H2O water, and they found out that the number of molecules in their thimble of water was about 1.6 times 10 to the 23. And they went to compare that number with the number of people on Earth and asked the question, how many orders of magnitude separate the number of molecules of water in a thimble with the number of people on Earth? And they actually did it in a slightly different way than the way that we did it when we did it as a group a moment ago. So let me have you explain what you did differently to compare these two numbers. What'd you do?
What did I do? Okay.
Yeah.
At what point, B3?
Yeah, this was B3. We're comparing molecules in a thimble of water to a number of people on Earth.
I figured that it had to be at least about 14 orders away, because from 9 to 23.
Okay, so you're saying let's, instead of comparing the whole numbers, let's just try to compare these exponents.
Yeah,
So it looks like there's about 14.
Because we're not starting from 0 like we did in the first example.
Okay.
And then from this, I just skipped the step of dividing both of them in the log.
Okay.
So I did the log of 1.673 times 10 to the 23rd.
And what'd you get for that number, by the way? So in other words, this group is taking logs first instead of dividing first.
And that was 23.2234.
Okay.
And then I took the log of 6 times 10 to the 9th and got 9.7782.
Okay.
And subtract those two numbers to get 13.445.
Okay. So you took those two numbers and then you subtracted them. And got 14 point what?
13.44.
13.44, thank you. Okay. Okay, but this wasn't exactly how we did it before. How did we do it when we did it a moment ago? Right, the log of the quotient. So the way that we would have done this is by taking these two numbers, dividing them first. So 1.6723 times 10 to the 10 to the 23. Whoops, looks like I got a typo here. Divided by 6 by 10 to the 9th. And then we got a number, and then we would have taken the log of that number, log of the quotient. But on the other hand, what this group did was they took the logs of the numbers individually, 1.673 times 10 to the 23, and the log of 6 times 10 to the 9th. And they just subtracted them. But in fact, those two answers will be and will always be exactly the same. And the reason for this is that if we just start by taking the logs, instead of starting by dividing, starting by taking the logs, what we're really finding is we're really finding which tick mark on the linear number line these numbers would occupy. By taking the logs, we reduce the number 6 times 10 to the 9th to the number 9.7782, which is between 9 and 10 on a linear number line. And likewise, the number 23.2234 is between 23 and 24 on a linear number line. So by taking the logs first, we've turned our log scale into a linear scale. And once we have these numbers on a linear scale, then how do we measure the difference? Subtract. Right. So if we convert to a log scale from log to linear scale first, then we can subtract. So take the logs first and then subtract. On the other hand, if we keep the numbers on the log scale and compare them there, then we have to divide. But then once we've divided, we don't get a number of steps right away. We have to then take the log to get the number of steps. So either way turns out exactly the same, and this is a generic property that holds true for any logarithm, that the logarithm of a the logarithm of a quotient, the log of x divided by y, is the same thing as the log of x minus the log of y, whenever those logs are defined. So the log of a quotient is the same as the difference of the logs. So either one of these two ways is a perfectly valid way to compute the number of orders of magnitude, the number of steps separating two numbers on a log scale.